We start this course with a review of probability. And we start our probability review with very early fundamental concepts. So let's start at the beginning. The intuitive concept of probability is relative frequency. If you did an experiment a whole bunch of times, you had a certain outcome, so many of those times, you kind of think of the probability of that outcome as that fraction. How often did it happen out of all the opportunities? And if you just pick, say, a coin toss, the probability of a head is this ratio of the heads, how many heads out of how many total tosses, and you let the number of tosses go to infinity. I mean, that's the intuitive concept. You can't do a real experiment an infinite number of times. And we'll say the toss outcomes can only be heads or tails. If it bothers you that it could land on a side or something, that we'll just call that an invalid toss. It's not a toss. So that the only possible outcomes are head or tails. If you added those probabilities, say that's what probability means, when you add them, they just add like this, because it's either a head or a tail. It can't be a little bit of both, or some mixture of both. So when they're mutually exclusive, they just add like this. And the sum of limits is the limit of the sums. In this case, at probability of 1, because in this case, head and tail are A, mutually exclusive, and B, those are the only possible outcomes. That's everything you could possibly have, either a head or a tail. I'm saying all that because they're going to lead to axioms. Because we can't go much further than this. I mean, we can't really take these limits. These are just conceptual. But by the way, if you say that the probability of a head is equal to the probability of a tail, if you force that to be, then this arithmetic from above says the probability of each one is a head. That's an outcome of this assumption. But we'll take these characteristics of probability and try to make things a little bit more rigorous, because somebody said, let's treat these things and let's use some set theory so we get some math we can get our hands on. I'll call these dots in here, they represent outcomes. The easy way to think about it is if you toss a die, you would have 6 possible outcomes by how many spots are facing up. 1 spot, 2 spots, 3 spots, 4 spots, 5 spots, or 6 spots. So those would be your outcomes for a die toss. Outcomes, they're mutually exclusive. That's by definition. The set of all possible outcomes is your sample space, usually denoted as S or script S somehow. Events could overlap. They don't have to be mutually exclusive. An example of a die toss, an event could be the number of spots facing up is even, an even number of spots, even number of spots. Another event could be the event that the number of spots facing up is more than 3. So events are subsets of the sample space. The outcomes are subsets of the sample space. The outcomes are mutually exclusive. The events do not have to be mutually exclusive. And then we're going to define a probability measure three axioms. First, the probability of an event is greater than or equal to 0. If you go back to this intuitive idea, the probability of any outcome out of all possible outcomes can't be negative. So that's one axiom. Another one is the probability of the whole sample space, meaning the union of all outcomes, meaning if you do an experiment, you're going to get at least one of the possible outcomes, right? You're guaranteed to get an outcome. So the probability of the whole sample space, the whole set, is 1. And the probability of a union of these events that are mutually exclusive anyway, disjoint, mutually exclusive, is just the sum of the individual probabilities. So these are the three axioms of our probability measure. And we start out thinking in terms of sets and outcomes and events and subsets. From those three axioms, we get these 5 theorems, I guess more, which map from your sample space onto the real line. This bar overhead of an event A means complement of event A, which means all outcomes in your sample space that aren't A. A is also a subset. So A bar, or the complement of A, is also a subset of your sample space. The probability of that is 1 minus the probability of A, and vice versa. The probability of the event A is 1 minus the probability of its complement. The probability of the null set is 0. And you got to get one outcome, do an experiment. This theorem, the probability of a union of events, where these events can now be overlapping, they're not necessarily mutually exclusive, is the sum of those two probabilities minus the probability of the intersection of those two. A and B are both subsets of your sample space, and A is a subset of B. And the probability of B is greater than or equal to A, or probability of A is less than or equal to B. And for any event in S, the probability of that event is between 0 and 1. This is a theorem that is derived from the axioms. We didn't make that an axiom. So what the probability measure does is map events in your sample space to the real line between 0 and 1. And that's all I'm going to say at this very beginning. We'll continue in the future.